Professor, are you there? The fuck? Is it just me that doesn't hear audio or see anything visually?
I don't hear anything or see anything either.
Okay, just wanted to make sure. Thanks.
Hello, Professor. Hello. Professor.
Yeah.
I had a question. Like, I joined a bit late today. Are we gonna have a quiz today? Hello.
Oh, yeah, we do. The slide didn't show?
Yeah, the
Uh,
wasn't showing the whole time, and I didn't hear you. I was trying to text, but there's nothing.
I just see lecture 7.
Oh, huh. Sorry. Uh, so okay. The quiz will be waived for everyone. For some reason, I did not hear anyone either. Hmm.
Oh, my apology. That's very weird. All right. Uh, that is very strange. Somehow the screen sharing is not working. All right. Wow. I'm really sorry. I did not notice that the screen sharing wasn't working all this time. All right. So here's the deal. So we will waive the quiz today. Everyone will get a 10. And let's take a break. After a break, we'll start, I guess, working from problem 1 or problem 2 again. All right. So I did not realize that somehow the audio and the video did not come across the whole time. All right. I really apologize. I will check this more carefully next time. Okay. So let us resume at 7:05. Okay. And then, sorry. Yeah, 7:05. And then we'll restart again. Sorry about that. All right, so let's start again. Again, I'm really sorry about this. I did not know that Zoom was frozen. So if this does happen next time, please, I think the moment someone speaks into the microphone, I hear it right away, right? But if you chat, type in the chat, like I said, I don't check the chat, or I cannot see the chat on my iPad, so I cannot fix it right away. Again, it's my fault, but it'll be fixed faster, right? If you speak in the webcam, because I would be able to hear something right from the system. So if it happens next time, I think please try to grab my attention that way. That
Professor, I spoke
yeah.
into the mic in the beginning and also like maybe 15 minutes into, and
Oh,
I'm,
you did?
yeah.
Yeah, I
so
also responded to that at the time.
that's so weird. Oh, I really apologize too. I did not hear anything either when you speak. That's so weird. There's something wrong with my system then. Okay, no, then completely my fault. I should have checked, double check at the beginning. I'm so sorry. I did not hear anything until I think Neil started speaking, asking about the quiz. I'm really sorry. Completely my fault. I don't know why that happened. So you did speak in the system, because this happened before in my other classes, and somehow when someone speaks into a system, I can hear it. But anyway, I guess it's water under the bridge. I'm very sorry about this. Cannot say anything else. Okay, let's do it quickly to kind of catch up from where we were at, and I will promise double check every time we start the session. Okay. It's completely my fault. So since this is the case, I will keep this in mind when I write your midterm too. I will make it reasonable. All right, that's my promise. Since it's really a bad mistake. All right, so I will go through what I was speaking about during the first half quickly, right, to save time. And again, right, if there's anything that unclear, right, please ask. But basically, we were discussing, right, the problems in the problem set. We did this last time, right? And the answer is no, not the density. Okay. And the reason is because this changed sign, okay, over 0 to 5 halves. Okay. As can be seen, right, when you look at the sign of 2x minus x cubed. Right. So x equals to 0 and x equals plus minus square root 2. So, right, 0, root 2 minus root 2, right? And here's 5 halves. So whatever the sign is here, right? Once it crosses square root 2, it will change sign. So if it were plus, it will be minus. If it's a minus, it will become a plus. So it changes sign, so it cannot be a PDF. The same analysis would follow here, but we just look at 2x minus x squared is equal to 0. If only if x, right, 2 minus x is equal to 0. So 0 and 2, right? But you see 2, right, is still below 5 halves, correct? So whatever sign it's here, it will change sign. So, right, it still change sign over 0 to 5 halves. So the answer is no, cannot be a P. So that's the answer to number 2. All right, any question about this one? All right, so the next question, right, is about this. So I'll give it maybe 30 seconds, right? So you can take a look at the problem. And so, right, what is the problem about? So we are given a random variable, right, x, that describes what? That describes the volume of cells, right? Right, and the density of x is given like that, right? Like so, right? That's the density. What are we asked for? We're asked for the capacity of the tank, right? So that blah, blah, blah. So question, capacity, right, equals question mark. Now, we should note here that capacity, right, is a constant. Just in case, right, you know, we think that we're looking for an variable, but right, capacity is a constant. But we must determine this capacity, so what? We must determine this capacity so that the probability of the supply being exhausted is so much, right? So just kind of like, you know, relating the context, the concept here, right, is connected to the concept of VAR, or value at risk, in finance, where a bank or financial institution must decide what kind of reserve, which you see right here, they have to keep, right, so that they don't run out of reserve, right, over a week or over a day, which is the sales here, right? So that's the same concept, or sorry, not that they don't, but the probability that they run out of reserve is small, right? Some small number like 0.01, right? And so the probability of the supply being exhausted, right, you might think about a little bit, but it's going to be that, right? The probability that the weekly demand is beyond the capacity. Okay. One thing you should note is that this is not just P of X equals to C. That's wrong, right? It's wrong simply because, right, the weekly demands is a continuous random variable. So probability X equal to C is 0. So that's not possible. It's not that possible, but it doesn't make sense, right? So what you are looking for is probably the weekly demand is at or above the capacity, right? Of course, it should be noted that the capacity is between 0 and 1, right? And now we need to write this in terms of the given density, right? And how do we do that? Well, remember that the density, right? The density is related to the probability like this, right? To find the probability that X is between two values, you integrate the density over those two values. And so the two values here, right, is of course C and 1, right? Because X is bounded by 1. Or, you know, if you want to write down even more completely, it's like that. This actually is redundant, right? Because X is always less than or equal to 1, but it reminds you, right, to be able to write down the integral as C to 1. Like that, right? And we need to set it equal to 0.01. Right? And from there, you can solve for C. Is that okay? Any question about this? All right. So then the next set of problems, right, require us to discuss the concept of the expectation of the random variable, right? But before we do that, I think there was some, so this is the discussion, right? There was some kind of like reiteration, right, of the concept we went over last time. I just want to kind of discuss. The first iteration, right, is that a CDF is not a antiderivative only, okay? So in other words, right, the CDF, while it's true that differentiating the CDF gives you the PDF, to find the CDF, right, it is a definite integral. Or in other words, you have to figure out what the integrating constant is to decide the CDF exactly, right? If you don't, then you will get the incorrect result from, let's say, this problem number 1, right? Like this. To find the CDF here, right? So if you remember from part A, we have C to be 3/4, right? But it's not correct to say that this is 3/4 x minus x cubed over 3, which is the mistake I made last time. Because, right, basically, this is just trying to take the antiderivative here, right? But that's wrong, because it's missing, right, this integrating constant that will make it into a correct CDF, right? So the correct way to do so is to integrate from -1 to x, right, to pick up the integrating constant as 1/2. Right, so that's the first thing I want to remind you of. Right. Any question on this? The second thing, right, is that the CDF is very important when we deal with continuous random variable, right? So the reason is because the PDF is not a probability. And so to work with probabilities, then the only thing that we can work with is the CDF in continuous random variable. In discrete random variable, you don't have to worry about it because the mass function is already a probability. But in continuous random variable, right, that's not the case. So because you have the PDF, so you have to be careful and pay attention to the CDF. Okay. Finally, right, the topic that actually you just saw in problem number 1 and problem number 2 in the worksheet, that sometimes a density can be given with an undetermined coefficient. And why is it the case? The reason is sometimes people like to work with a shape, right, and do not want to spend the work to find out what the area under curve is of the g function, right? Of course, abstractly is very easy. Just take the area under the curve, take the inverse, but some functions is not very easy to integrate. So they just work with the undetermined coefficient, right? Of course, right, as long as the function does not change sign, then that's a valid approach. But with, for example, right, problem number 2, right, even the undetermined coefficient is not enough because the function changes sign. So there's no coefficient that can fix that. Is that okay? All right. So then the next topic we look at is the expectation of a continuous random variable, right? And the formula for it, right, or the definition is you will integrate, right, the x against the density dx over all values in the support of the random variable. And this is very similar to the discrete case where you sum, right, over all values in the support of x, the same x, but now multiply with probability x equals to x. So now you see the link is, right, the sum is the integral, right? Basically, integrating is continuous sum. The probability, right, x equals to x actually is like the density times the dx quantity, right? So again, the density alone is not a probability, but the density times dx, right, is approximately a very small probability. If you look at this, let's say picture, right? So if you have a single bar, not a bar, right, a line, and that's not an area. But if you move a little bit in terms of dx, then that's an area, and that's a probability, right? That's approximately close to probably x equals to x, but you know. So that's the meaning, right, of the expectation of a continuous random variable. Right. Any question about this? So as an example, right, we ask to find the expectation of a uniform distribution. So a uniform distribution, right, has constant density, right, which is 1 over b minus a over the interval a to b, right, and 0 otherwise. So its expectation is the integral over, right, this interval x dx times the density, right? So here, I guess I put the density after x, but it doesn't matter, right? That's the density, that's x. And if you integrate this, right, you'll see that it's equal to b squared minus a squared for the x over 2, right? And then b minus a is here. And if you simplify this, right, because of the factorization, then you got this b plus a over 2. So the expectation of a uniform, right, is a plus b over 2. Well, does this make sense? It does make perfect sense as the interpretation of a center of mass of a piece of wire, right? If you have a piece of wire with constant density, then from A to B, then you expect, right, that it's center of mass, or you put a needle, right in the center, right at the center, then that will balance, right, the piece of wire, right? Of course, this is true in general if you even change the density over an interval, right? This concept still works. But at least for the simple case of the constant density, we can verify, right, with our intuition that it agrees. All right. Any question about this one? So then when we move to expectation of a function of a continuous random variable, the same or a similar thing applies to the discrete case. That is, right, to take expectation of a function of a continuous random variable, you take that function, evaluate all values of x, times the density at those points, and integrate over the whole support, right? It's very similar to the discrete formula, right, where we, instead of integrating, we take the sum, right, and then probability, right? And we mentioned, right, that back then, right, that this is the law of the unconscious statistician, meaning it's a theorem, right? And it's still the case here. The reason is because if you want to do it by definition, then you have to find out the density of the function of x here, and then use that density to integrate rather than doing this with density of x, right? And as I mentioned here, figuring this out is not easy. This will be a part of our discussion in this lecture, right? But nevertheless, the law of the unconscious statistician allows us to calculate this very easily without having to figure out the density of phi of x. Any question on this one? All right. So the properties of expectation is still the same under the continuous random variable as the discrete one, right? That is, it's linear, right? And it's linear, doesn't matter what the connection between x and y are, right? And so here you start to see that expectation is expectation. Whether, right, we use the formula of an integral or a sum or something else, if it's a mixed distribution, it's really about computation. Like, how do you get to that number? But the properties of the concept of expectation holds across all random variables, whether it's continuous or discrete or something else, right? Namely, that it's linear. Doesn't matter how the summands are connected. And so as an example, right, we have these two random variables, and we ask for expectation of ax plus b and expectation of ax plus by. And here I pose the question, right? What is ax plus b? In other words, do you know the PDF of ax plus b? If you think a little bit about it, you may be able to figure it out, right? Namely, that if x here is a uniform, then ax plus b here is also a uniform. So you can figure out, right, the density, etc. By the way, right, this a and this a are the same. This b and this b are the same, which might seem a bit weird, but doesn't matter, right? We can still do the calculation just to demonstrate the concept. But the point is, right, you do not even have to figure out the PDF of ax plus b, because if you just follow the linearity, then you got the answer to be this. Not having to figure out what ax plus b is in terms of random variable, right? Even more dramatically, when it comes to ax plus by, you can ask the same question. What random variable is ax plus by? Is it a uniform? The answer is no, right? In general, when you add two uniform random variables, you will not get a uniform back, even if they're independent. But notice, right, here, you're not even given the relationship between x and y. And the point is, it's not needed to calculate the expectation of the sum. Because again, right, by linearity of expectation, you can just break it down to individual terms and plug in what we've known about the expectation of a uniform. Any question about this? Okay. And so the higher moments, remember we have a slide like this for the discrete random variable, and it's exactly the same. In this case, just replacing sum with integral, right? And probability with density. The variance is exactly the same. Notice, right, the variance here does not even reference PDF directly. In other words, as long as you somehow can calculate the higher moment, then you can calculate the variance. Of course, right, to calculate the higher moment, you need to figure out you need to use a PDF to figure out. But if you somehow look at the variance through the concept of expectation, you don't even need to reference the PDF directly. Why do I say this, or why do I mention this? The reason is because the properties of variance here, you have seen it once in the discrete random variables, and it's exactly the same properties. And the reason exactly is because this definition is the same for both discrete and continuous random variables. And so it's not surprising that the properties of the variance are the same, right? Doesn't matter. So in fact, right, a lot of these that we talked about are universal across all random variables, whether discrete, continuous, or something in between, right? Any question about this? All right. So here I mentioned that, right, in this example, both x and y have expectation equal to 0 because, right, you can add them up, right, the average value is 0. But the variance of y here, right, is 100 times bigger than the variance of x. As can be seen, right, from the variance formula for uniform, which is b minus a squared over 12. And we will show that when we look at the uniform distribution. But, right, this example is just meant to show that the variance does measure, right, the spreadness of a random variable, right? The more spread out, the higher the variance. Any question? All right. So now let's take a look at the next one, which is the new one, right? So computing expectation, right, of all of these random variables. So let's take a look at, I think, B and C first, and then we'll look at A later, right? For example, let's take a look at B, right? Here, the expectation will be the integral from -1 to 1 of some constant, right? We know what that constant was, right, from the previous question, but some constant times x dx, all right? So the question is, what is this value? What do you think?
Is it 0 because the symmetry?
Correct, and that's what you should do here. This is an odd function. So the integral over -a to a of a function that is odd is equal to 0, right? Remember, an odd function means f of -x is minus f of x, all right? So the point is, when you do this integration, you should utilize all trick, right, up your sleeve to make your calculation easy. C, right, nothing much here, but it's going to be the integral from 5 to infinity, right, of x, 5 over x squared dx, right, which is the integral from 5 to infinity of 5 over x dx, right? Well, do we remember the antiderivative of 5 over x? That's ln, right? So what's the answer? What's the final answer here?
Is it diverging?
Yeah, it's infinite, right? And here, right, you see actually there are random variables whose expectation is infinite, right? Here's one example, right? And that may or may not seem strange, but that's actually it happens in probability, right? You can have something whose average value, right? It's infinite, right? Here's an example. Okay. And now let's address A, right? The reason why we save A last is because, of course, it is integration by parts, right? Now, you know, whatever you want to do here, right? So you can do integrate by parts and you will get an answer, right? What I want to show you is another technique, which is legitimate in this class, which is to utilize the knowledge of some other random variable. By the way, right? This approach may or may not work, meaning that you must somehow see that this fits some other random variables that you know. It's not guaranteed to work, okay? Because whatever, maybe, meaning that it's not like it will work incorrectly or whatever, but it may not fit, right? Whatever the integral you're looking at may not fit the random variable that has been known. So what random variable are we associating this with here? So this is kind of looking ahead, but we will cover the exponential lambda, right, later on, where for the exponential lambda, the density is lambda e to minus lambda x for x positive. All right. So the density of an exponential is lambda e to minus lambda x. What's special? What's special is you can use without proof, because it's kind of established that expectation of an exponential lambda is 1 over lambda. And the variance of an exponential lambda is 1 over lambda squared. You can use it without proof. All right. So now let me ask, do you see how you can utilize this knowledge? And the some random variable here refers to exponential to do a quick calculation of this one. Again, right, you can do integration by parts. That's valid. But is it possible to utilize the knowledge of the exponential random variable to not do as much work?
Well, you could let the lambda be x over 2.
No, lambda is a constant here. So lambda is
Sorry. It's just 1/2.
correct, right? So if I let lambda be 1/2, then what is this? What am I looking at? Because right, without knowing what value I'm looking at, right, I cannot associate this with these, right? Or let me be blunt. Is this the variance? Is this the expectation? Or what is it?
I think it's a half of the expectation.
This?
Yeah.
Nope. Because this is lambda
Oh,
e to mass lambda x, and this is,
they're x squared. Yeah.
yep. So the answer is this is 1/2 expectation of x squared, where x is exponential 1/2. Do we understand? So that's the first step, right? That's not the last step yet, but that's the association. Right? Any question about this? Why this is true? Right? Because you do 1/2 here, right? And 1/2. And this 1/2, e to the minus x over 2 is the density of an exponential. And then x squared, right, is expectation of x squared. Right? Any question about this? Now that's the first step, right? That's not done yet. Now you have to know, you have to say what this is, right? So what is the final answer here? According to this piece of knowledge. Now you can get to use this piece without proof. What is it?
It'd be the expectation minus the variance, and then times 1/2.
No.
Oh,
So expectation of x squared, right? So remember, this expectation of x squared minus expectation square of x is going to be equal to
The
the variance. So the expectation of x squared is the variance plus the expectation square, right? And in this case, right, what is it? The variance is 1 over lambda squared. So that's going to be 2 squared, right? And the expectation square of x is 2 squared. Correct? So that's 8. So the final answer here is do we understand? Any question on this? So again, right, the point is, like I said, you do not have to use this approach. But, right, if you can use it, it can save you the actual work of doing integration. But you have to be super careful. Because sometimes, right, the mistake is to misidentify. And if you do, right, for example, you misidentify this as exponential 1/4. I mean, I don't know, for whatever reason. Or you misidentify this as expectation of x, then the whole thing is, of course, incorrect. All right. But if you identify correctly, in this case, for example, like this, then you can use the knowledge that has been established about these calculations. And that's the advantage of this approach. That's all there is. Right? Okay. Any question here? Okay. All right. So for this question, right, let's just point out very quickly, what do we need to do here? Well,
Take the
expectation,
integral.
yeah, the integral from 0 to 1, right, of x a plus b x squared, right? And that would be 3/5, right? But is that enough for us to find a and b?
We have to check that the density function like doesn't change signs.
Oh, that's fine. It's I guess kind of implied here, or basically, right? Here there's a and b, so you cannot really check that really. But what's at the issue
Oh,
here
okay.
is you need another equation, right, to find a and b, because you have two unknowns. And so far we only have one equation. What is the other equation?
Can you check the bounds of it because it has to go to 0 like outside of this area? Maybe.
No, that's a good point, but no, big error. Sorry, that's a very, what you said is a good thing to say, but it's a big error. What you're assuming is that the density is a continuous function, right? Because you say it has to go to 0. The answer is no. What's an example? The example is the uniform, right? The uniform has this so right, you see the uniform does not go to 0 outside the bound in any sense. What you say actually is correct for another function. You know what that is? The CDF. The CDF is continuous.
Professor, for this one, is it just like, is it the integral of f needs to amount to 1?
Yeah, that's it. That's it. The integral is 1. That's all, right? But this is actually a good error. I mean, I say big, but it's a good error. Okay. So the PDF doesn't have to be continuous. Don't make that mistake. But the CDF is continuous. So that actually is what's relevant, for example, in number 1. In the number 1 here, the CDF is continuous, meaning it starts from 0, it rises somehow to 1 after that, whatever the shape is. Right, sorry, it should not be decreasing, but right. So that's correct for the CDF. The PDF doesn't have to, okay? But yeah, here you just have to take the two integrals and like that, you will get a system to solve. Okay. Any question about this? Okay. Okay. Now let's take a look at this. So at the heart of it, right, the expectation here is nothing crazy, right? Of course, the point is, can you calculate this quickly? And how do you do that? So remember, right, an exponential lambda has density lambda e to minus lambda x for x positive. So what does this look like? Right? Which is expectation of y squared, where y is exponential, one. Right? So therefore, this will be variance of y plus expectation square of y. I guess you can do 1 square here if you want, but so I'm not claiming that the integration by parts here is hard, but you could avoid doing that even to do this. Are we okay here? So a cautionary thing here, right? If this is changed a little bit, like say starting from 1 instead of 0, right? Of course, this may not be a density if it starts at 1 with this, right? I'm just saying you might have to fix it, right? But then the integral from 1 to infinity of something here, just because of this, it cannot be an exponential. So just a small change in this direction will spoil this approach. So it's a good approach, but don't be super impressed by it and kind of, use it without being careful. Right? Are we okay with this question? All right. So the next one is uniform distribution. So I think that would require us to take a look. All right. So kind of, right, we have started discussing the uniform and stuff like that. But, right, exactly like the program of the discrete random variables, we will now start discussing the specific random variables, namely these guys. These are not on the program in the sense that you do not need to know. It's there to kind of showcase some well-known distribution, but you don't need to know this. Like you're not required to know this for this class, all right? These are the ones you need to know, okay? So let's go over the uniform quickly, right? We have talked about this a lot, right? Like that. So you need to know that its density is constant. Its expectation is exactly in the middle. The variance, right, is like this. And so let's see how much time we have. All right. So let's show you, right, why the variance is like this. Well, to find the variance, right, we need to find the expectation of the squared, right? Which, as you can see, is just x cubed over 3, right? But b cubed minus a cubed also factors, right, into b minus a squared plus ab plus b squared. So the answer here is a squared plus ab plus b squared over 3, right? And so the variance is this guy minus this guy squared, right? So a squared plus ab plus b squared over 3 minus, right, b plus a squared over 4. And you can see why the over 12 happens, right? So you got 4a squared plus 4ab plus 4b squared, right? And then minus 3, right? A squared plus 2ab plus b squared. Everything over 12. Correct? And the cancellation happens that this is 4a squared minus 3a squared, you got a squared. 4ab minus 6ab, so you got minus 2ab. 4b squared minus 3b squared, so you got b squared. And of course, that is that. Yeah, right, b minus a squared over 12. Or a minus b squared over 12, right? It's the same thing. Okay, any question? All right, so we'll continue next time with this. Let's just kind of quickly say, right, that it's used to model, right, the arrival time of an event uniformly, right? You have no knowledge. So bus arrival usually is the favorite example to use as a uniform distribution. Okay. All right, any question? All right, again, I deeply apologize, right, for the first half of the class. I will make sure, right, this won't happen again. All right. So sorry about that. But let us continue on Monday. Okay.